Okay.
Can you see something?
Yeah, I can. That's fine.
Yes. When seminar starts, I'm going to introduce you first.
Okay.
Then also I'm gonna briefly introduce your background.
Okay.
Then I will terminate the screen sharing so that you can start yours.
Okay. That's fine.
Then yes, then you can have a whole hour for yourself.
Okay.
Then after you finish, then please return the host to me. Okay. So I have 1 or 2 slides to show to students.
Okay, that's fine.
And generally, all graduate students in various areas.
Okay.
You know, not only from battery, but fuel cell, materials science, and etc. So perhaps they would like to hear you a little bit easier when you said and slowly and slowly.
Don't worry, I'm not known for lecturing very quickly, so it's fine.
Yes. I know you have many experience on this sort of situations. And after your seminar, I'm going to send you an email with a paper, which is the agreement of counseling. They call it counseling because the administration building will provide your honorarium. So they want to have, you know, all necessary documents. So what you do is you sign you print out first, then sign it and make a scan and send the scan file to me.
Okay, that's fine.
Yeah, that will be perfect.
I can do that.
Yes, in the agreement, the administration building wants to have sort of your permission to share your recorded video to academic purposes. As I explained to you earlier.
That's fine. I've deliberately put in things that are published. So I'll talk about that. So it's not a problem. You can share it.
Okay, wonderful. That's very nice. Then we have another almost 10 minutes. So what I'm going to do is I'm going.
You might want to stop the recording and then restart it.
Oh, do I do that? Anyway, the departmental staff will do that, I guess.
Oh, okay.
And I'll stop the screen sharing. So you test your screen sharing.
Okay. Yes, if you let me share mine. Okay. Share screen. I'm going to go. PowerPoint. Share.
Okay, I can see something. Yes.
Okay,
wonderful.
So that's fine.
Yes, wonderful.
All
then
right,
you can, okay. You can have this whole page.
I will do. I'll fix that so that it's the whole page when I start.
Okay, wonderful. Okay, wonderful.
But I just wanted to make sure the sharing worked before we needed it. Okay.
Yes.
So I'll stop sharing now and give it back to you.
Yes, wonderful. Then, and as I mentioned before, all graduate students will attend, and also many professors in our department and perhaps other department may join us for seminar.
Yeah.
So total number sometimes 70 to 80 people.
Oh, that's very nice.
Yes.
Yeah.
So
good.
Then
I'll have to get the university to update my picture since I grew my hair from lockdown.
well, this looks fine.
I couldn't get my hair cut for like 18 months, so it grew.
18 months.
So.
It's fine, no problem. You look great.
Thanks. Yeah. So, are you going to manage to travel to any conferences this summer, or will you have to
not this summer? I don't think I can do that. Perhaps in October or November.
Okay.
There is a couple of conferences, one in Tokyo and one in, where is it? Either Taipei or Singapore. I forgot.
Yeah.
And that's about it for this year. So fortunately, we are going to have ISA meeting online.
Yeah, yeah.
Yes.
Yeah.
That's right. So how often do you visit states?
I used to go to visit my mother twice a year. With the pandemic, there was a whole year that
I see.
And I'm going to go see her again on the 1st of June now.
Okay,
so
wonderful.
I saw her in
Yes.
September, and I'm going to go see her on the 1st of June now. So
okay, wonderful. That's very nice.
She lives in Michigan.
Michigan.
Yeah.
So that's why you attend the University of Michigan.
Yeah, it is. Yeah.
Oh, I see. Even though you were born in Berkeley.
Yeah, yeah. So my father was a PhD student in chemistry of Herb Strauss.
Oh, I see.
Yeah, it's in spectroscopy, and
yes.
Yeah. So I take after my dad when it comes to my work.
Oh, so your father was.
My mother breeds Siberian Huskies, so maybe at the end I'll invite my dog in to say hello to your students.
Okay.
So everybody who sticks for the whole talk can meet my dog.
Okay.
So that's the temptation to stay for the whole talk. You've got a black bar over part of the slide there, Hasuk.
What?
On the right-hand side of the slide, there's something on top of the slide.
There is I can remove that.
Yeah.
Whatever
it is.
Yeah. This way you don't see any, right?
Yeah, that's good. Yeah.
Yes. So normally I have just one picture so that the speaker will appear here. But somehow okay, now I can see you only.
Okay, good.
So when I talk, my photo will appear.
Oh, okay.
And there is some noise from some students. So
yeah, we'll have to remind everyone to turn their microphones off.
Yes. So now.
So while we're waiting, if we could remind all the students that the abstract submission
the
for the annual meeting.
Seminar supposed to start 4:30. So it's a little bit earlier.
We're a little bit early, so. But I'm just saying, while we're sitting here and people are listening to us, I'd like to remind everyone to submit their abstracts for the ISE annual meeting.
Yeah, right? Why don't you do that? Yes.
Yeah, so please submit your abstracts, right? And we want to make it's an online meeting. You can do it from your home. And the ISE online meeting works really well. So it would be lovely to see more people submit their abstracts. We've got quite a few in already, but it would be lovely to have some more. And for students, especially for students, the registration fee is not very great. So.
Yes. And also the registered participants will get next year's membership fee waived.
Yes, right. Yeah, so it's worth it.
So I advise all students turn off microphone. Still I can hear some noise.
Yeah, I think you might be able to mute them if you look for them. There's somebody whose name is SOOIK.
Yes.
And their microphone is not muted.
Okay, there is a message on chatting panel. Ask students to turn off microphone. Now SOIK, turn it off. Yes. Okay, now it's time. So I'm going to start seminar. So I hope you are ready, right?
I'm ready.
Yeah, welcome students and professors to our regular seminar on Thursday afternoon. And as usual, today we are going to have a very rare occasion to invite Professor Andrea Russell of University of Southampton, United Kingdom. And her title, I will say her title first, X-ray spectroscopic studies of electrocatalysts and battery material. And before she starts seminar, I'm going to, wait a minute, why, okay, I'm going to introduce her briefly. Actually, she was born in United States, living in Southampton now, and got her BS degree from University of Michigan, Ann Arbor, in chemistry department in 1986, then PhD from University of Utah, Salt Lake City in 1989. And after her PhD, she was appointed as a NRC, National Research Council postdoctoral research fellow, U.S. Naval Research Laboratory in Washington for 1.5 years, a little bit more than a year. Then she went to United States and served as a lecturer first at University of Liverpool, and then second part at University of Newcastle upon Tyne. Then he got Southampton position, studying as a lecturer, then promoted to senior lecturer in 1997 to 2004, then promoted to reader, same department, same university, then promoted to professor at physical electrochemistry since 2007. And during that period, she served as the head of Electrochemistry and Surface Science Research Group of University of Southampton. She got numerous awards. First one perhaps is Roselle Postgraduate Scholarship in 1986, then Stopper Prize for Outstanding Incoming Postgraduate Students, 1986, and Patricia Harris Postgraduate Fellowship for Women and Minorities in Underrepresented Fields, funded by U.S. Congress during 1986 to 1989. Then NRC Postdoctoral Fellow 1990 to 1992, and then Royal Society Industrial Fellowship in 2005 and through 2007. She has published more than 126 papers, 5 book chapters, 2 patents, and her research interests is application of spectroscopic methods to understand structure property relationships, which I believe is most important area in electrochemistry. And in detail, in-situ structural characterization of electrocatalysts and ion storage battery materials. Then recently she started surface enhanced Raman spectroscopy, especially in substrates and their applications. And please welcome Andrea. Let me finish. Okay, now it's all yours, Andrea.
Thank you very much for the kind introduction, Hasuk. It's a great honor to be able to present a seminar to you today, especially since I can do it without the jet lag. So by just moving from the top of my house.
Yes.
So we're in my home office today. So allow me to share my screen now. And then I'm going to go slideshow from the start. Okay. So in preparing this talk, I slightly changed the title because I realized I was going to have way too much to talk about after especially after I talked to Hasuk about the background of the students and postdocs and faculty that will be attending this talk. So I'm just going to talk about the X-ray spectroscopic studies of electrocatalysts. And Hasuk, is my volume okay?
It's good.
Okay, good. All right. So so I'm going to talk about in situ. Let's see if I can get a pointer here. Laser pointer. Okay, there we go. So I'm going to talk about in situ X-ray absorption spectroscopy. And to do X-ray absorption spectroscopy, we have to have an X-ray source, and we generally use synchrotron radiation. So the scale of this diagram is completely out of kilter because this is a great big building. Okay, so this is the synchrotron ring, but we take the X-rays that come off the ring, we go through a monochromator to choose the energy that we want. In the studies I'm going to show you today, they all use a double crystal monochromator to choose the X-rays. We clean up the beam with the slits. We have to measure the intensity of the X-rays before we go into the sample. And then we can either measure our data in transmission, so we measure the absorbance, or we can measure the fluorescence. One of the great things about using X-rays as our spectroscopic probe is that they're very penetrating, and that allows us to collect the data either in situ or under operando conditions. And I'm a real believer that we need to make a distinction between these two terms in spectroelectrochemistry. So in situ, I mean under electrochemical control. And if we were to say operando, what we're doing is really approaching the true working environment of the material. So if you're doing battery electrodes, it's easy to do operando studies. If you're doing electrocatalysis, it's much more difficult because the fuel cell or the electrolyzer usually has a very large volume. Well, the electrolyzer usually has a large volume of electrolyte and the X-rays can't get through it. For fuel cells, we would have to go through the field flow plates and things and the current collectors. And that makes that difficult. So the data that I'm going to show you today are really in situ measurements, but people use these terms interchangeably now. And I'm not an advocate of this. I think we need to make this distinction so we know what we're talking about. The advantage when we start looking at these complex materials that we're now using in electrocatalysis is that we can collect the data from the perspective of each element. So I'm going to give an example of a platinum tin catalyst. And they were able to collect the data from the perspective of the platinum and the tin. And by looking from both directions, we understand the material in much more detail. I'm going to show you in a moment a slide which gives you a picture of the overall spectrum, but we break it up into two parts. We call this part the XANES, and that's the X-ray absorption near edge structure. But that's the energy of the transition. And there's a few extra features in that can tell us about the oxidation state and the coordination geometry, right? So for example, if you have a metal ion in an octahedral or a tetrahedral site. The XAFS, the extended X-ray absorption fine structure, is the rest of the spectrum. And that gives us the average local coordination environment. And it's really important that we remember that this is the average. It's the per atom average. The picture here on the left is just a picture of the electrochemical cell that my group has developed over the years that allows us to study quite a number of different electrode materials. It's not perfect for everything. And I have a PhD student right now for whom this cell is just not working and we're going to have to make him something else. But I showed this is the I0, so we're measuring the beam over here. I transmission is over there. And this yellow bit is the fluorescence detector. So you can see we have the cell situated here in the middle. We've got the reference electrode coming in by a rather long bridge. So not perfect. There's always a compromise. In all spectroelectrochemistry, there's always a compromise between the needs of the electrochemistry and the needs of the spectroscopy. So X-ray absorption spectroscopy, this is a core electron spectroscopy. So here if we're at the L edges, for say platinum, we're exciting the P electrons in the core, the 2P electrons. The X-ray energy is scanned until this transition occurs. And the electron is then leaves the absorber, the absorbing atom, and is promoted to above the Fermi level. So it leaves the atom and goes out, it's going to interact with the surrounding atoms. Right at the energies of the transition is the Zanes region, and the wiggles that we see out here are the X-apps. So we can interpret the Zanes in terms of the position of this edge and the intensity of this thing we call the white line, which is the first peak beyond the edge. So the Zanes is going to give us oxidation state, and where we have changes in the white line and we're working at the L edge, we can say something about the D band occupancy of the atoms, of the metal. The X absorption's fine structure, these wiggles, we're going to analyze those to give us the local coordination. So thinking a little bit more of what's happening. So the X-rays come in, the absorbing atom absorbs the X-rays, the electron is converted to a photoelectron. It then leaves the neighboring atom and goes out and collides with leaves the absorbing atom, goes out and collides with the neighboring atom. And there it backscatters off the electron density of the neighboring atom and comes back. And so could I just ask students to please ensure they have their microphones off? Okay, so we have interference between these two waves, and where it's constructive, the absorption is greater, and where it's destructive, the absorption is reduced. And that gives us those oscillations as we change the energy of the X-rays. To analyze those wiggles in the X-apps, we have to fit that data to this equation. And I'm not going to go through the equation in great detail. I just want you to recognize the parameters that we are fitting. So we're fitting the coordination number here. So we know how many neighbors of that type are surrounding our absorbing atom or absorber atom. We know the distance to them, that's here and here in the equation. And then we have a mean square disorder. And what's really nice is that the distances are in the frequency part of the data, whilst all the parameters are in the amplitude. So when you're looking at X-ray absorption spectroscopy and people have fit the data, they normally report the distances fairly precisely. But the coordination numbers always have a reasonably large error bar, and that's because they're coupled. All right, these terms are coupled to one another and cannot be separated unless we can collect the data at a large number of temperatures and then fit it. And I want to do my work in situ in an electrochemical environment. So I can't go to liquid nitrogen temperatures or I'll freeze my electrolyte and nothing will work. So in situ X-apps of electrochemical samples, we have to accept that we have error bars here on this coordination number. So let's take a little bit more of a look inside the cell that my group normally uses. So we often use a carbon paper-based electrode, and we've painted the catalyst, for example, or our battery material ink onto this carbon paper. And that's the working electrode sitting here in the middle. We make contact to it with a gold wire or another wire if we're going to look at gold, right? And then there's an X-ray transparent window sitting on top of this that's usually capped on. So this is the underside of the cell. The counter electrode is sitting back here behind the cell. So they're concentric, but with the counter electrode a little bit displaced, right? And the solution will then flow through here. We sometimes put filter papers across the working electrode to ensure wicking of the electrolyte across the electrode. It really depends upon the hydrophilicity of the ink that we've made. So we pump the electrolytes in and out, which means that we can circulate the electrolyte, and then our reference electrode comes in here. So that's not ideal, but it allows us to use a proper reference electrode on the beamline. You could put, say, just a palladium bead that you charge with hydrogen to make a palladium hydrogen reference electrode. You could just have platinum wire in there and have a platinum pseudo-reference electrode, but we like to use either a mercury sulfate or an RHE electrode. So what does it look like? If you've never been to a beamline, what does it look like when you go to put your cell on the beamline? Well, our cell, one of our cells, it's a different one, is sitting right here. So you can see most of the rest of this is the rest of the equipment. So you've got the x-rays coming from the x-rays are coming from this way. This is all the monochrometers. This is measuring the incident beam here, I0. There's your IT, your transmission beam. We can also do diffraction at the same time with this curved detector if we wanted to, and our fluorescence detector is sitting over here at the side. All of these big bits of equipment are provided by the synchrotron where you're visiting, and hopefully you're working with very good station scientists who will help you set it all up. When I first started in synchrotron work back in the 1990s, working at the NSLS in Long Island in New York, we had to do all the alignment ourselves, and things were not very well controlled. These days, the beamlines are usually very well aligned and very well controlled, and so you don't have to do that bit of the work yourself, but it's why you should put the beamline scientist as an author on your papers, acknowledging all the work they've done to help you make your experiment a success. Before I launch into talking about the X-ray absorption spectroscopy of the 3 systems that I promised in my abstract, I want to just take you through what the data look like. And I have a beautiful example, probably one of the best examples in terms of the clarity of what you can see is happening, came from the PhD of one of my students, Stephen Price. And with Stephen, what we were looking at is how you can make core shell electrocatalysts. And here we're using a gold core. We're going to deposit copper on it, and then we displace the copper by galvanic replacement, which is something that Radoslav Adzich at the NSLS has really pioneered. So what are we doing? So we can collect the data either from the perspective of the gold atoms, or we can collect it from the perspective of the copper atoms. So let's look first at the perspective of the copper. So this is the X-ray absorption spectrum, and we're going to look in the Zanes region, and you can see that as we deposit the copper, the dashed line here and the blue line are the spectrum of the copper when it's just in solution. So that's the copper 2+ ions, the solvated copper 2+ ions in solution. The black line here is the spectrum of copper metal, a foil. And you can see that as we change the potential and deposit the copper onto the gold, the spectrum shifts from being of the copper species in solution to approaching something like the metal foil. It never gets all the way to the metal foil because the copper atoms don't have their full 3-dimensional structure of all the coordination that they would do if they were part of copper foil. So you can see that the edge energy is shifting, right? As we change the oxidation state, it shifts, go from copper 2+ to basically copper 0 or almost copper 0. We're watching the edge change. We're watching this white line is decreasing as well. So we're looking at the effects of the change in the coordination as well as the change in the oxidation state. So you can gain a lot of information just by looking at the Zanes region. If we then isolate the X-half spectrum, what we see is when we're up at plus 0.2 volts in this case, where we really have the copper ions in solution. And then as we go negative, we're depositing the copper ions onto the gold surface. The oscillations here, the frequency of those oscillations has to do with the coordination distances. The decay in those oscillations, how they decay as we increase in K space, this is K, angstroms to the -1 space, which is an energy space. But as we go along in K space, you can see that initially the oscillations really decay very quickly as we go out into K space. But when we've made the copper atoms sit on the gold, you can see that it's extended these oscillations. So what this is telling us is that in the first case, we have the coordination is quite short distances, longer period oscillations. We can tell that the neighbors are low atomic number, so probably the oxygen atoms of the water. So those neighbors are low atomic number, so that the backscattering is very damped, so we don't see as much of it. And so this really tells me I have copper in a low Z, a low atomic number coordination environment, with the distances being quite short, right? Then when I start to put the copper on the gold, what happens is the period of my oscillations decreases. So my distances are the longer than the metal distances, but the damping goes away. So I see the oscillations are sustained out to higher K. And that's telling me that the atom that the photoelectron is bouncing off of is heavier. So you can see this in the raw data. To interpret X-ray absorption spectra, the X-halves part, we take the Fourier transform. And so here's the Fourier transforms of those, and the red lines are the fits. So you can see we start off with some neighbors that are between 1 and 2 angstroms, and we gradually move to having the neighbor, the coordination environment is moving so that the neighbors are at longer distances. Now these are not phase corrected, so you can't just read the distances off the plot, right? You need to fit the data. But again, it's showing us that we're going from these hydrated copper ions to copper sitting on the gold. So that's the perspective of the copper ions. And you can clearly see in this set of data the key features in terms of analyzing X-ray absorption spectra. If we looked from we could fit all the data, right? And we can see that so these are the parameters you would get out if you fit the data. We had the coordination number. You can see that the errors are pretty large, right? As I said, because it's always coupled to this Debye-Waller factor. But for the distances, we know them quite precisely, which is why we can confidently say that there are 2 different oxygen distances around those copper ions, right? And you can see that as we go more negative, we lose the oxygen coordination and we gain copper-copper. And we gain copper-copper when we have the highest coverages, but we initially just have copper on the gold. One of the beauties of X-ray absorption spectroscopy is you can look from both directions. And in the case of looking from the gold, we see something that's really interesting. So if we're not depositing the copper onto the gold, what we can see is that the particle shape of the gold particle sitting on the carbon is potential dependent. So we see variations in the X-halves spectra as we go from one potential to the other, and you can clearly see things are happening. We take the Fourier transform. Hopefully you can see that there is a bit of difference in the shape of this Fourier transform, especially when you start looking out to the higher shells. And what this is telling us is that the shape of the gold particles is changing as a function of the potential. And that's really interesting because mostly in electrocatalysis, we treat those metal nanoparticles on a support as static blobs, right? We think of them as having a defined shape and they're just sitting there and that they don't change. And I'm going to argue that many of the degradation processes that we see as we cycle these catalysts through oxidation and reduction in terms of aging is also because the shape is changing. The amount that the particle wets the carbon surface changes as a function of the potential. And so what we see is they go from being quite flat, the positive potentials, and as we go negative, they become much more round or spherical. What happened, just to finish this story before I launch into the proper part of my talk, is if we look from the perspective of the gold, though, in terms of depositing that copper on the surface, we really never see the copper in the coordination sphere of the gold. And this is because these particles are quite large. They're sort of 3 to 5 nanometer particles. And so you remember that X-halves is a per atom average. So the average coordination environment, even we put quite a bit of copper on the surface of these gold particles, is still that the gold just has gold neighbors, right? The fraction of the atoms that are gold that have copper neighbors on the surface is very small. And so from the perspective of the gold, we never see that the copper's there. But what we do see is that we still get the shape change in terms of particles. Okay, so now I've introduced X-ray absorption spectroscopy. If we start thinking about trying to apply this to real electrocatalysts, there are some characterization challenges that we need to recognize, right? Are you working on well-characterized model catalysts, or are you working on commercial materials? If you're working on a well-characterized model catalyst, you may be able to restrict the particle size distribution in terms of your nanoparticle size. And that will allow you to interpret your data more easily, right? If you've got a very wide particle distribution, when you have a per atom average, the big particles actually get weighted more in your XFS analysis than the very small particles. So you need to be careful. Also, in terms of commercial materials, you may have different composition ranges. And so you really need to think about what you're looking at. If you want to get structure property relationships out of the data, you need phase pure samples to yield those relationships. You then want to know that that structure is retained when you start working under in situ or operando conditions. And actually you can learn a lot by just having these model systems and see whether that structure is retained. So for our gold particles, we saw that the shape of the particles changed. It's really important that every atom of the edge that you're looking at is active under the in situ or operando conditions. So we have to be very careful about loadings. We want a thick enough or loaded enough electrode that we get a good X-ray absorption spectroscopy, so we're getting good signal to noise. But if it's too thick, then maybe not all the material is going to be active. So if I have a very thin electrode, then a catalyst layer, then I might think that all of those atoms of the catalyst are going to be active. As I make it thicker, then I'm going to have to worry about where my interface is with my electrolyte. Okay? And so it's always a compromise. The spectroscopy people will tell you you want more sample in the beam to a limit. But the electrochemists are going to say, but if I make it too thick, then I just won't know what's going on. You have to worry about the porosity. Are you getting good diffusion through your film? And you have to worry about, as I said, the particle size. The smaller the particle, the more surface sensitive the measurements are going to be. And in terms of a catalysis, it's pretty much going to happen at the surface. Finally, when we get onto these oxide materials, we're worried about oxygen as our first shell neighbor. It's low Z. We saw that the spectra are going to decay very quickly as we go out in energy space. So it's tempting to not bother to collect higher K space data. And that's always a mistake because it makes it more difficult to normalize your spectra and subtract the background. But it also means you're not helping yourself when it comes to calculating the spectra for higher shells. You need a bigger data range if you want to be able to have more parameters to fit. So make sure that you're paying attention to each of those aspects when using X-ray absorption spectroscopy. Okay, so come on, oops. It doesn't want to advance. Give me a second. Next slide. Okay. So the first of the samples that I promised to talk about is platinum tin. And we started looking at this by making a platinum 3 tin material using the polyol synthesis method. So we made a family of samples, and this was done by a postdoc in my group named Abu Nassar and a PhD student named Haolong Huang. And we made these samples by using the polyol synthesis. So we take the parent sample and we anneal it differently. So if we anneal it in air, argon, or hydrogen, what we do is we exchange the extent of mixing of the materials and of the atoms in the nanoparticles, such that if you anneal them in air, the sample looks very much like a platinum sample in terms of diffraction. When you anneal them in hydrogen, you really mix the materials and you get the platinum 3 tin that you'd expect. You see the peak shifting, and that allows you to calculate the extent of alloying using Biegard's law. If we look at the Zanes, let's look at from this perspective of the tin now. What we can see is that as we anneal, we go from something that really looks like tin oxide, that's the orange. So we're going to anneal in hydrogen. We're bringing this down so that it's looking closer to tin foil. It never gets there, right? But it's moving that way. So we can see that we're changing the oxidation state of the tin. We looked with XPS, and XPS is a little bit more surface sensitive, but when you're talking about nanoparticles, it's not completely surface sensitive, but it allows you to see that we are indeed changing the oxidation of the state of the tin as we change the alloying. So in air, argon, and hydrogen. So the air is a really poorly alloyed material. The tin is mostly present as tin oxide, and the hydrogen is a very well alloyed material where the atoms are really mixed. Finally, we can do the XAFs and collect the data from the platinum edge and the tin edge. And then we fit that data simultaneously, right? So that the platinum tin and tin platinum distances must be the same. So that helps you fit all the parameters that you need. And that gives us another measure of the extent of alloying. And so what is the extent of alloying? Well, each of those measurements gives you a different measure of that. And so by having them all, we can say that if you anneal under hydrogen, you get a pretty good, but not perfect platinum 310 alloy. It's always a little bit tin deficient. If you anneal in air, it's pretty much platinum particles with a little bit of tin oxide. And if you anneal in argon, it's somewhere in the middle. So why would we be interested in platinum tin as an electrocatalyst? Well, it's interesting in the fuel cell environment for improving CO tolerance, but also as a catalyst to provide us with an active oxygen species in terms of, say, methanol, ethanol, or butanol oxidation. So if we look at the electrochemistry of our sample, so this is a platinum and carbon reference material. Here's the CVs of those that were annealed in air, argon, and hydrogen. And this is the CO stripping voltammetry. I assume that most of you are electrochemists, but if you are a thermal catalysis person, you can sort of think of the potential scale as the thermal axis in terms of doing temperature to programmed desorption, in terms of the red lines here, which are the CO stripping. In electrochemistry, we change the potential to turn that on. And what we're looking for is the lowest possible light-off temperature in terms of thermal catalysis, but the potential at which we start to see the CO oxidation, right, which we call onset potential in electrochemistry. And you can see that even if I have tin oxide associated with my platinum particles, I'm seeing that the onset potential has dropped, okay? And it continues to drop as I alloy. So the onset of CO oxidation is decreasing with the addition of the tin, which is well known from the literature, right? So that's good. We're getting the information we'd expect. It's interesting if we can measure the electrochemical active area by the area under these peaks, or the area having associated with the hydrogen adsorption or desorption peaks in the CV, right? And we can see that for the tin-containing catalysts, the CO area is greater than that of the hydrogen area. And this suggests that the tin, there's some tin on the surface of these particles that may be blocking the hydrogen absorption sites, but the CO sites are not blocked. Okay, so that's interesting. Just to show you that we use these materials to look at methanol oxidation. We also looked at ethanol and butanol, and you can see those in that Faraday discussions paper. But again, you see that as you change the extent of mixing, you pull the onset for the oxidation of the methanol down in potential, right? I don't really want to compare the peaks because I'm now having to worry about mass transport effects as well as just the fundamental thermodynamic effects. It's interesting to look at these two plots though, because this one is the specific activity where I have normalized this by the surface area of the platinum that's available, and that was done by measuring the area of the CO peaks, versus mass activity. So this is the fundamental activity of the material in terms of the catalysis. This is what it's going to cost you. Those of us in academic science are very interested in this and trying to develop structure activity relationships. We are very interested in specific activity. The companies we work with are really only interested in mass activity, right? So this is how much current I'm going to get for every gram of platinum I have, right? And you can see that the effects are a little bit less when we start to consider that. So how is that CO activating? Well, the second metal is thought to undergo by this bifunctional mechanism. So the second metal alters the strength of the platinum CO bond. That's the ligand effect in thermal catalysis. It activates the oxygen at a lower potential. So that's a promotion effect in thermal catalysis. And by varying the bulk and surface composition, we should be able to separate these two. So we want to understand the importance of tin in terms of its availability. We want to know if the alloy is really necessary. And finally, we want to know whether the tin oxide can play a role as a co-catalyst. And that set of experiments I've just shown you wasn't controlled enough to isolate each of those effects. So Howard, or Xiaolong Huang, who was my PhD student, had a really good set of ideas. What we're going to do is we're going to make some platinum tin catalysts, and we're going to do it without alloy formation. And so we can do that to either isolate the tin atoms or isolate the tin oxide. We did this isolation of the tin atoms by using a surface organometallic reaction to deposit the tin on the platinum. And we're going to use really low coverages. So this catalyst is not meant to be a commercial catalyst. It's a model catalyst that's going to allow us to explore this phenomenon. So we're going to have very low coverages, and we're going to deposit this by reducing the platinum in hydrogen, and then adding this species, the butyl tin, under nitrogen. If you want to reproduce these results, please be very careful that you have completely removed the hydrogen gas before you add the butyl tin, and do it all under nitrogen, or it will catch fire. We can similarly take our parent platinum on carbon and add tin stannate. If we reduce that under room temperature and hydrogen, we can just leave the tin oxide decorating the platinum particles without forming the alloy. So what do they look like? So here's the tin that's decorating those platinum particles. And you can see that we have no alloy, as evidenced by the X-ray diffraction. The particle size distribution stays nice and small. We can look from the paraspectrum of the TEM and the Eels mapping, and we can see that the tin is really sitting on the surface of the particles. So that's lovely. That's with 0.2 monolayers. Let's look at the electrochemistry. So with the electrochemistry, we can see that as we increase the amount of tin in the CO stripping, we're pulling the potential at which that CO stripping starts more negative. So we're getting the effect we want. You can see in terms of this, the blank CV without the CO, you can see that the oxide formation is being pulled down to lower potentials, and we're suppressing the hydrogen peaks, right? So very nice. So it looks like the tin is really sitting there on the surface. Its redox activity is maintained, and we're seeing this effect we'd expect in terms of CO promotion. So of course, we did the X-ray absorption spectroscopy, and of course, we're going to do it as a function of the potential. So in an in-situ environment, so we can see that from the tin perspective, the edge is shifting more negative as we reduce the potential. So we're reducing the sample, or shifts more positive to higher energies as we oxidize the sample. Here, instead of showing you the amplitude of the Fourier transform, we're showing you the phase, because it really points out the differences here in the tin platinum coordination as we go from the case where it's at the most positive potentials, where it's really the tin oxide. See that that's all decaying, and we increase now the number of metal neighbors as we reduce the sample. So if we start here from we'll start from the negative potential. So we're sweeping this way. We can see that the tin has the oxidation states the red. It has mostly platinum neighbors, right? So we have tin decorating these platinum neighbors. And as we increase the potential, we're oxidizing it. We've got OH on the surface. And I'm probably talking way too slow, so I'm going to have to speed up a bit here. We have OH on the surface. Eventually, we make a tin oxide. And what this allows us to show is, because we can run the CVs repeatedly, we know that this tin is providing this OH species to oxidize the CO, but it's turning over, right? So we can see that it keeps turning over. When we looked from the perspective of the tin oxide decorated sample, so here's what the sample looks like. You can see the platinum with the tin oxide particles. When we look from the perspective of the platinum, it is really just platinum particles. We look from the perspective of the tin, it's tin oxide, right? Again, we still see the effect though, in terms of the enhancement of the CO oxidation, right? And we can see that again, it can be sustained, right? And what the data showed then was that this OH sitting on the tin near the platinum is really mobile. So in platinum tin electrocatalysts, one of the reasons companies have not been so keen on pursuing this is they were worried if you go to too high a potential, and that's where you go to when your fuel cell's at rest, right? When the oxygen is allowed to permeate through, then you reach these higher potentials. And people worried that as the tin dealloys, that you're losing all your activity. And what these data suggest is that you don't need the alloy, right? That as long as the tin oxide remains in good contact with the platinum particles, you will still enhance your catalysis. All right, so I'm not going to go through the conclusions here because I pretty much stated them as I've gone along. So moving on, let's look at some oxide materials. Now life's going to get much more difficult because the only neighbors I have are oxygen, right? And it's really going to be hard to see that second coordination cell to see the heavier metal neighbors. So this is a PhD project of Peter Richardson in my group. We've never published these results for a variety of reasons. But he made a series of iridium ruthenium materials. Ruthenium oxide should be the most active, and that's been known for a very long time for the oxygen evolution reaction, but it's not very stable. So what we tend to do is add iridium, which is less active, but more stable. And he made this series of samples. And the nice thing is that we were able to keep the particles pretty small. If we look at the activity of the materials, most people do rotating disc experiments where you take a thin film, catalyst film, on your rotating disc. So by dropping the ink on the catalyst, you can see that the ruthenium has the lowest onset potential for the oxygen evolution reaction, and iridium is over here. The mixed materials are in between, right? Don't think about the currents over here, because in these rotating disc experiments, these currents over here are really dominated by resistance. So you really need to think about where the thermodynamic part of the kinetics is affected. We can make these samples up into a proper water electrolyzer cell. This was in collaboration with a company called ITM Power. And we ran the experiment at 60 degrees C under 20 bar. So it's a pressurized cell. And they're only interested in high current density. So this is 1 amp per square centimeter. What you can see is that the ruthenium is indeed the most active material. It requires the least over potential to get the greatest current density. And iridium sitting up here. But again, our mixed materials are sitting somewhere in the middle. So the trend is still there. When you run them for a long period of time at 1 amp per square centimeter, though, you do see that the ruthenium starts off well, but after 500 hours, its activity begins to fade. Whilst the iridium-based materials, even with a little bit of iridium, with only 25% iridium, you have a much more stable material. So what's going on? Well, we can look at the oxidation state of the ruthenium from the zanes, and we do that by looking at the edge energy position. And we've made a series of reference compounds, right? So these are all of my reference materials. I know the oxidation state of the ruthenium in the reference materials, and that allows me to calibrate the edge energy to give me the oxidation states. I can do the same thing with iridium. Here we tend to use the peak position instead of the edge position. But again, I can have my 3 reference compounds with different oxidation states of the iridium, and that allows me to create a calibration plot. And so we then did the experiment under operando conditions. And do I have a picture of the cell? No, sorry. I must have cut the cell picture out. But in the case of this cell, because we're going to really be evolving oxygen, we had to flow the electrolyte much more to get the bubbles out of the cell. So there's a slightly different cell design where the electrolyte is purged much more rapidly. What we can see is as we change the potential, if you just start off with iridium sample, the edge is shifting. So the oxidation state of the ruthenium is really changing, right? But when we add the iridium, we suppressed that oxidation state change of the ruthenium. So we're stabilizing it somehow, stabilizing the ruthenium. If we look from the perspective of the iridium, for the iridium oxide only catalyst, first of all, it doesn't change oxidation state much itself. Its oxidation state is a bit different when it's mixed with ruthenium. So we are getting some electronic interaction between the ruthenium and the iridium, which might account for the enhanced activity of the iridium atoms in the mixed material. Okay, and you can see, but it really is, their oxidation state is different, but it doesn't change very much with potential. And so what we think happens is that when you have the mixed material, you get an iridium enriched surface. And this is also something was found in some thin film studies by Wang's group, right? So you see, if you have iridium sitting on the surface of the particle, so make a ruthenium pore surface, you get enhanced activity. And so we think the enhancement here comes from the fact that the ruthenium in the underlying layers is increasing the activity of the iridium on the surface. So finally, I want to talk very briefly about some perovskites as oxygen reduction catalysts. And here we're going to look at the manganetes, right? And so there's been a lot of work that looked at how the manganese B site cation is the active site, and that it's been proposed that the activity is reliant upon the turnover between this manganese 3 and the manganese 4 couple, right? So you need to be able to keep accessing this whole loop if you want to get the full 4 electron reduction of oxygen to make water, as opposed to being trapped here in the 2 electron reduction. So where you're going to make the peroxide species. And that activity has been shown to be influenced by which A site cation you choose. So, and that A site cation may be cobalt, nickel, lanthanum or calcium. The nickel here is the B site cations. So if we're looking at the manganetes, we might have a mixture of lanthanum and calcium, all right, and other mixed species. But we find that the lanthanum manganate itself, when it's a little bit oxygen deficient, provides us the best material. And why is this one the best? Well, there's various activity descriptors in the literature. It has to do with the redox couple, right? What potential can you go between these two? It has to do with the number of d electrons and the EG orbital occupancy. In this case, we have a partial occupancy of that EG orbital. So there's only 1 electron in it, and that seems to give us the best descriptor in the literature. So we wanted to study these materials, and the problem is mostly they're made in terms of, well, people have done a lot of thin film work, but that's not very good for the way I do experiments. So I need a particle material. And most of them, the synthesis is by a sol gel route, and that gives you really big particles, and then you just don't see anything. So, or a co-precipitation route. So we came up with, in collaboration with the people at Bristol, this method. And what it uses are the aqueous nitrate precursors, but then we use this ionic liquid as the solvent, and then we add cellulose, right? And that allows us to make the perovskite structure with very small particle sizes, so we have a large surface area. We can show as we go, we made this is the work of Veronica Kilaria from my group and that of David Furman's group in Bristol. And we can show that as we can make the whole series of samples as we go from lanthanum manganate to the calcium manganate. The calcium manganate, the EG orbital is unoccupied. Well, lanthanum manganate, the EG orbital is occupied, right? And so we're seeing this range. So here's just the TEMs to show you that she's got really nice, pretty small particles. Now, as someone who started off with metal nanoparticles, which I can have between 2 and 5 nanometers, these seem pretty large to me, but they're not the bowling balls that you get from some of the other methods of hundreds of nanometers in diameter. Let's look at the change of oxidation state as we change of the oxidation state of the manganese as we change the composition, because we would expect that to be the case. So the lanthanum manganate is sitting down here when we have that increased EG occupancy, and the calcium manganate sitting up there. So these are our samples. So, and then we have the calibration curve made from some reference materials. And so you can see that we do indeed see the edge shift. There's also some interesting changes in the octahedral structure here that can come out from further analysis of the zanes, right? But we're seeing the average oxidation state of the manganese ions changing as we would expect as we change the composition. Let's look at the oxygen reduction activity, and this is the rotating ring disk experiment. So here is the disk where we're reducing the oxygen, but the products then travel out to the ring and we can oxidize those. And we can see that the calcium manganate turns on at the most negative potential. It's the least active material. And that as soon as this oxygen reduction turns on, the peroxide formation also turns on. So this is the oxidation of the peroxide. So that's that mechanism. With the lanthanum manganate, it's really interesting. We get onset at much more positive potentials. And only when we get to these potentials do we start to see the peroxide. So there's a slightly different mechanism going on in this region than that region. Okay. And we looked at the effect of changing the content on the mass activity and the specific activity. So we don't get monatomic trends, and this lanthanum 0.8 is really less active than we would have predicted from the EG occupancy. We then looked at the intrinsic activity by thinking about the amount of the manganese ions that are active, right? And that made more sense, right? So it's the fraction of the ions on the surface of the particle that allow you to understand it in more detail. But really, I was blitzed through that because I want to talk about this really new method that we can look at these complex samples with X-ray absorption spectroscopy. And this is by using the X-ray emission spectroscopy. So normally what we do is we do the fluorescence and we collect all of the fluorescence photons from all of the different possible fluorescence paths. So this is just showing the K beta emission, but we normally collect the K beta and the K alpha emission. So we collect a wider range of the fluorescence signal to try to get the best data in terms of the X-axis. But if we use a second monochromator to ensure that we're only collecting the emission from this pathway, then we can get greater sensitivity so that we then collect the emission spectra. So we're now looking at the K beta emission spectra. And as we change, these are our reference compounds, you can see that we've got two peaks here. So we've got the K beta 1,3, which is the constructive spin pairing between these, gives us this enhanced peak here. And the destructive spin pairing gives us enhanced peak there. And I encourage you to look at the paper for the details. But in terms of electrochemistry, what this is telling us is this peak shifting to higher energy as the oxidation state decreases. And this one is losing intensity, right, as this total spin of the 3D decreases. So again, that's the occupancy of that d orbital. So here is our lanthanum manganate and our calcium manganate as a function of potential. And you can indeed see that we're seeing the shifts in these peaks, right? And we've got more information here is the important part. When you did the oxidation state from the edge position, you only had one parameter, so you can only fit one parameter. But I want to fit the population, not just the average oxidation state. And so by doing this and fitting the data to our references, we can then fit the spectrum as the components. And what we can see is that for the lanthanum manganate, the average oxidation state was 3.5, and it was made up of 71% manganese 4, 11% manganese 3, and 17% manganese 2. And as we change the potential, we reduce the sample, the manganese 4 is going to manganese 3, the fraction of manganese 2 is not changing, right? So that tells us several things. My surface area is not great enough to account for all of this change. So the subsurface manganese must be redox active, but it's also telling me that I'm not accessing that manganese 2. I'm not wandering off from where I want to be. To maintain activity, I need to stay manganese 4, manganese 3. The calcium manganate, on the other case, started off with an average oxidation state of 3.7, and it's easily over-reduced, right? So we wind up with making much more of this manganese 2. And that's reflected in the XAF spectrum of the Fourier transforms of the XAFs region. You can see from the lanthanum, as we reduce it, the shape, the amplitude of the oxygen, manganese oxygen coordination is decreasing, but the overall structure as reflected in these higher shells is not changing, right? So I'm not losing my perovskite structure. With the calcium manganate, as you reduce it, because you over-reduce it, you lose that structure. These peaks are really different from those. So we've had some significant structural disruption, right? And we can see that when we look in the post-mortem XRD. So we dried out the electrodes and looked at them. After the electrochemistry, we've still retained the perovskite structure. But here, for the calcium, we don't. And we're really making something that's much more like manganese oxide. So I know I rushed through this last part. I'm hoping the first part was worth it. But for the ruthenium-iridium mixed catalyst, we think this enhanced stability is because the iridium protects the surface, but also that the activity of that iridium at the surface is enhanced by the ruthenium being subsurface. For the manganates, it's this really, the access of this manganese 3, 4 plus redox activity gives you the best catalyst. And you want to avoid over-reducing to form manganese 2. So that EG occupancy is still a good descriptor of the activity of the material. And I encourage people to start exploring these new techniques using X-ray emission spectra. And it allowed us to gain more information than the single parameter we could fit with just the Zanes. The work that I've done, shown you, covers about a 4 or 5 year period in my group. And so the acknowledgements are extensive in terms of funding and beam time from a wide variety of people, of sources, but also people. And fortunately, the people for both projects are mostly listed here. But thank you very much for your time. And I'm very happy to answer any questions. So thank you very much, Ashok. I need to stop the show.
Well, thank you, Andrea, for your wonderful presentations. You have shown beautiful application of X-ray absorption related as well as X-ray emission spectroscopy for the catalyst characterizations. And student can ask any questions now. Then I'll switch to professors later. A student can send questions through chatting panel, not necessarily in English. I can translate.
I'm hoping I didn't talk too fast at the end.
Yes,
I always go too slow at the beginning, and then I have to accelerate. So.
Well, while they are preparing questions, I have one simple question for you. And the last example, lanthanum manganate catalyst, you have shown the reduction of oxygen, and I believe it is 2 electron processes.
Is a
2 electron process. 2 or 4. Or you mean both?
Yeah. Well, it looks like from our rotating disk electrode experiments that you initially have something that you're reducing something, right? It's rotation rate dependent, so it has to be coming from the solution. So you're reducing oxygen initially. When you start to form more of the manganese 3 on the surface, then you turn on the 2 electron process. So we think we've got the 4 electron until you start to have too much manganese 3 on the surface, and then you turn on the 2 electron process. So it goes from one to the other.
I think the potential of ring electrode is to monitor the hydrogen peroxide, isn't it?
Mm-hmm.
And then
yeah. So if I were to share again, I can go back to that slide.
Yes, please.
Okay, what you can see is for the length, I fully agree with you that by the time we get to these potentials, right, we are starting to be dominated by the 2 electron process.
Yes.
But here, when I have the lanthanum manganate and the ones that are lanthanum rich, what I'm seeing is I am getting reduction current, and this current is rotation rate dependent. So I'm certain it's not just I'm not just recording the reduction of the manganese, right? But so I must be reducing something. I believe it's oxygen, because if I don't purge it with oxygen, I don't see this, right? And so I think up here where you maintain good access to the manganese 3 plus 4 plus redox, then you do get the 4 electron cycle. But as soon as you go too far negative and start having more manganese 3 just sitting on the surface, so if you go back to the mechanism, you wind up trapped in this loop, and then you're wind up with the 2 electrons. So certainly, I would agree at these potentials, you're seeing the 2 electron. But up here, you may be able to access the 4 electron process. So the key would be to not drive it too hard. So it doesn't mean that it suggests that, it's not a super duper material for oxygen reduction, but in terms of understanding the fundamentals, then yeah, that's what it suggests.
Okay. Well, I'll stop at the moment,
good
and
question.
I will ask you another question later.
That's fine.
Let students ask you anything. If not from students, then how about professors? So they all
So you're all just,
understand completely.
or I was completely ununderstandable and have confused everybody. So, is there anybody out there doing X-ray absorption spectroscopy in the group?
Well, some students do. Some lab in our department either planning or already started X-ray absorption spectroscopy as well.
Okay. Okay. Good.
Well, we have a beautiful ring facility about 2 hours away from our campus, a city called Pohang, and the Postec has the facility. And what we do is you bring your sample or your cell, then they set up everything there. You just mount your cell. Yes.
Okay. Yeah. That's
Okay,
good.
then let me ask you my second question.
Okay. Yep.
And concerning about the platinum tin for carbon monoxide oxidations. And you said that it is not necessary to have alloy formation between platinum and tin, and you observe the good activity as long as you have a good contact with platinum and tin oxide, perhaps.
Yep.
Yeah, and then what is the microscopic picture of the contact between platinum and tin oxide? Is it oxygen in between or metal, tin, and platinum?
Okay. Let me just share my screen again. The answer, Hasuk, is we can't answer that question from our experiment. All right, but let me just explain why. Okay, so here's our platinum particle, our catalyst particles. We got platinum particles, we've got the tin oxide particles decorating them, right? And we know that we really haven't made a mixed material, right? So we don't see tin in the platinum shell, and we don't see platinum in the tin shell, really. Okay, so it's very tin oxide, right?
Yes.
Okay, so we're quite certain that we have not made a mixed material, but we're quite certain that these particles are adjacent to one another. But we don't know how they're linked, right? There's too small of a fraction of those material of that, and there's no special labeling of the, say, the oxygens that would be between these to be able to link them, to be able to isolate that. So it would be very interesting to understand how these are interacting, but I don't see how our measurement can provide that information. What we do know is that this experiment's quite interesting, and I didn't explain it very well. This is a platinum disc, and what Howard did was he just added the tin oxide nanopowder onto the surface of that platinum disc. And you can see the enhancement here. So you haven't done any heat treatment. You haven't done anything to mix these materials. Just having the tin oxide sitting there on the surface, we see the enhancement of the activity, right? And you don't need very much of it. It's we see improvement even with the least amount of tin oxide on the surface. So, which just implies that the OH being formed on that tin oxide is really mobile. right? This is not strongly absorbed. It can run across the surface very easily. All right. And that was one of the really interesting bits of his research, that by thinking about breaking it up and doing the experiment this way, as opposed to just doing it where we were looking at the particulate catalyst, right, where we're getting the activity, to prove the point, he had the brilliant idea of doing this, right? Because there's no way I formed an alloy. I've only drop cast this on. I haven't done anything else, right?
So actually, even though we don't know the exact microscopic picture of the boundary between platinum and tin oxide, there perhaps is no electronic interactions.
Yeah. So I think it's really acting as a promoter.
Yes.
And
So
not, the ligand effect is not important here. When you get to doing methanol, butanol, etc. oxidation, then I think your ligand effect starts to become more important.
Yeah. Okay. Okay. Thank you. Thank you.
You're welcome.
And
there's one thing in the chat, maybe?
Mike, I am wondering if any of your methods can estimate. The one professor sent.
Okay. Yeah.
I
can read.
Yeah.
I'm reading the chat. Okay, so I'm sorry I can't turn on my mic. I'm wondering if any of your methods can estimate the percentage of protonation of the surface oxygens, the ratio between OH and O under operando conditions. And is that ratio for the platinum tin? Is that what this question is for?
Yeah, I think so, yes.
Okay. No, I don't think we can. We don't have enough. Yeah, there's a little bit of a clue. I don't think we can get what you want, but we can get close. So let me just share again.
Isn't it possible to quantify the SO of the carbon monoxide depending on the?
Yeah, I mean, you have to start really believing the carbon monoxide is a benign probe. Okay,
yes,
so if the carbon monoxide is a benign probe, you might be. But I think it's not. Sometimes it doesn't want to change slides. I think it's when I have the slides with lots on them is the problem. Okay, but I think this gives us a bit of a clue is that by looking from the tin perspective, and by having the really small coverages, so you know that you're not making a bulk tin oxide. So this is 0.2 monolayers, but we did the same things for the lower coverages. The data just gets noisier. What you can see is that, so we have an estimate of the, now it's going to move. We have an estimate of the ratio between them by looking at these. So we have the tin platinum coordination and the tin oxygen coordination. And so if you assumed that you only had this and that as your limits, it would give you a bit of the ratio. So so I think you can approach it, but I can't give exactly what you want, right? Anything else?
We have Professor Chang. Here is. Okay, thank you very much. Somehow she cannot use a microphone. That's why
that's
she
fine.
sends. Yeah, that's.
No, yeah. Especially if you're in a noisy area, it's hard to use your microphone.
And so there's a final call for questions to not only to students, but also to professors. As the time is getting fast. So it is close to lunchtime for you, isn't it?
Yeah. For me, no, it's only 9:45 in the morning. So I had breakfast before I did this. So it's close to having time to have a cup of tea.
Oh, is that right? Okay. Any questions? Anything?
Here we go. Maybe this will stimulate a question. Come here, Dusty. Come say hello to all these students. There you go. There you go. My dog says hello.
Okay.
All
Okay,
right.
then thank you, Andrea, for your wonderful textbook type presentations. Thank you very much.
You're very welcome. It's been great to meet you this way, Hesuk, and I look forward to when we can meet each other
Yes,
again
of course, of
at a
course.
conference in real
Yes.
time and share a cup of coffee.
Would you please close the screen share?
I will do. There we go.
Yes. Then what I can do is here I'm going to announce the next seminar, which will be on May 12th, same online, and Professor Kazunari Domen of University of Tokyo and Shinshu University. He has a second lab in different university, and they appointed him as a university professor. So university professor is higher up than ordinary professors. The title of his talk will be photocatalytic water splitting to produce solar hydrogen on a large scale. So I hope you can also wait for this seminar 2 weeks from now. And again, students have to make sure to remember that seminar report, 2 to 3 pages, is due by noon on June 23rd. You can, and afternoon, I'm not going to accept your report. Okay? and thank you everybody for your participation to seminar. And again, thank you, Andrea, for your beautiful presentation. Thank you. I look forward to see you in the near future, somewhere in the world.
Okay, thanks. Thanks very much.
Bye.
You all have a good day. Bye-bye.
Okay, bye. Okay, and 조교는 이거 출석부 다 만드셨으리라고 가정하고 오늘 일은 몇 명까지 70 몇 명까지 들어왔던데. 오케이, 그럼 세미나 마치겠습니다. 수고하셨습니다. 고맙습니다. I will see you 2 weeks from today. Bye.